Who's ready to take a nap? It's after lunch, and you got all that like Polish food in you. I just actually earlier went off campus and found a nice kielbasa stand. Nothing like having Polish sausage in Poland. So yeah, and then you decided to come to a talk on functional programming, because that's always exciting. Yeah, let's talk about functions and programming, because that'll be, yeah. All right, let's move on. One of the things when we start talking about functional programming, and by the way, the title of this particular talk actually comes, it's the same title as a memo. And a lot of people consider it to be sort of the root of the discussions around functional programming. Why functional programming matters was a memo by a gentleman by the name of John Hughes, and it goes back quite a ways. I don't think it was published before I was born, but it was pretty close. Somewhere in the 70s, if I'm not mistaken. And in it, he talks about why functional programming is important, why it matters. And so it seemed like a good way to sort of reuse the talk. But, you know, whenever we start talking about some of this stuff, it helps to begin from base definitions. So, okay, what's programming language? Formal language, as opposed to an informal language like most spoken language. Formal language designed to translate ideas into machine instructions, which then begs the question, what exactly do they do for us? And to be very blunt, what most languages end up doing is they choose a certain number of concepts that they want to capture, what we call a first-class concept, and expose that to programmers as a way to create things so that we don't have to constantly reinvent the wheels. The whole don't repeat yourself principle, the dry principle, which many people attribute to the Prags, actually has a long history, long before them. Pierce is author of an extremely dense book on types and type theory, types in programming languages. Each significant piece of functionality in a program should be implemented in just one place in the source code. Go further back. An introduction to programming with S. Algol. Any Algol programmers in the house? Come on, show of hands. Yeah. No? No Algol programmer? Turns out that was a significant concern for Algol, which in many cases predates all of us as programmers. Basic dictum that aims to reduce duplication of information in a program, usually with an emphasis on code duplication, whenever practical, by making use of abstractions provided by the programming language or software libraries. And then scheme, same thing. Structure and function should be independent. In short, most of these languages, regardless of the type of language you choose, whether it's object-oriented, dynamic, functional, procedural, line-oriented, line-numbered, whatever, all of these languages, their goal is to provide some abstractions that you can use to represent things once. The abstraction principle. Now, for most of us, that has been objects, right? Is there anyone in this room who is did not grow up, cut your teeth on object-oriented programming? Show of hands. There are a few of us old-timers who may have done some procedural programming before objects became the fad, but for most people in the industry today, objects. And we were taught a number of things about objects. This is the way that the world is modeled. This is the way that God thinks. When I hold up a thing, it is an object. And it has properties like color and soft foaminess thing. And we got the color here. It's got a number, a label. We can attribute things to this, but this is an object. And we can debate as to whether this should be a singleton object or whether there's multiples of its kind. We happen to have another one over there. But these are objects, and it's very clear that these objects have both state and behavior. It has a state, color. It has a behavior. I talk into it and everybody hears what I say. Or perhaps that behavior is not actually a behavior of this object, but this object's behavior is to transmit that data to another object whose job is to then transmit that data to other objects scattered around the room, which will then transmit that data to your ears. Even your ears are an object because that's what captures that data and then transmits it to your brain, which is another object. It is a world filled with objects. until it's not. Because one of the things that we frequently run into is places where objects seem to fail us. For example, how many of you have ever physically laid hands on a tax rate? I don't mean on the money used to pay the tax. I mean physically laid your hands on a tax rate. Objects should be real, right? They should be a thing. They should be something we can all agree on. How many of you have ever physically laid hand on a business rule or a validation? As a matter of fact, if you go looking through the Gang of Four book, you'll discover that there are a lot of objects in the world that don't really seem to correspond to objects. For example, how many of you have ever held a strategy in your hands? Or maybe you happen to have wandered across a visitor. I don't mean the kind of person that comes to your house and stays there for too long. I mean an actual visitor object. Or a decorator. Or a composite. Or a command. There's a lot of these objects don't seem to fit with the traditional object paradigm. And as a result, in some cases, traditional object solutions kind of seem to get away from us. For example, when we start talking about transactional processing, well, okay, yeah, that doesn't really fit the traditional object modeling paradigm, as evidenced by everybody's favorite whipping boy, Enterprise Java Beans. Because, EJB just sucks. But when is the last time you ever laid your hands on a transaction? Can I inherit a transaction from something else? What is the transaction's logical semantic parent? That doesn't even make sense to ask as a question. Functional programming, fundamentally, if you want to get up and walk out right now, functional programming is a different way of thinking about how we apply the abstraction principle. That's it, the end. Give me good evals, there's the door. Now, what that really means, that's an exercise in walking through some of those definitions, etc. But the key thing to understand, one of the things I hear, one of the reasons I hear people routinely citing, functional programming, it's so hard. It's for all those people who went to university and got computer science degrees and for data scientists and all that stuff. Just give me objects. Objects are intuitive and I understand them. Yes, because that's what you were trained on. Funny thing, most of the people in this room, Polish is intuitive. Alas, I am not one of them. My Polish is limited to dziękuję. That's it. That's all I know. It's not an intuitive language for me because it's not the language that I was born under. It's not my native tongue. For most of us, objects are your native tongue. So yes, learning a new way of thinking about abstractions is going to be hard. And so this is an attempt to try to give you some of these basic grounding principles so that when you walk out of here and suddenly run into a guy who does Scala or Clojure or even does Java, because it turns out functional programming has nothing really to do with the language you're using as much as it does the concepts. The language should make some of those concepts easier to use, but just like you could do objects in C, you can do functions in Java. So, some basic functional concepts, and we'll go over all of these. Immutable values, functions as first class, currying and partial application, expressions as opposed to statements, laziness. Typically, although not required, we will see that most functional languages will be strongly typed and type inferenced, meaning the compiler is actually better than you as to figuring out exactly what a given thing should be. Recursion, we typically have tuples and we prefer lists over arrays, which we'll get to in a little bit. And there's also typically a concept of pattern matching. And what do I mean by all of these? Well, first of all, immutability. How many of you have heard that immutability is a good thing and we should all strive for immutability? Yeah! Yeah, there's a couple of people like, yeah, and the rest of you are like, I'm too tired. Don't hurt me. How can, yeah. Stop hurting me with this immutability. The world changes, man. How can you possibly think about writing programs when I can't? They're called variables for a reason. They vary, duh. Well, it kind of turns out that, first of all, they don't vary as much as you think they do. If you start looking at your average Java program, written even before the functional thing really started to take shape. A lot of times we use a variable, we let it hold some value, but we don't often change it. Probably 50 to 75% of your code is already intrinsically immutable if only you'll let it. The problem in Java, very bluntly, is that to enforce immutability requires more work on your part. You have to actually type F-I-N-A-L. Oh my God. That's so hard. To have to type final int instead of int. Ah. And so typically, a functional language will choose immutability by default. So for example, when I say let x equal 0, this is just one of many different. This is not any particular language, this is sort of a functional pseudocode. But when I say let x equal 0, the language assumes that x will not change. It is assumed to be immutable. It's the inverse of the way Java makes its assumptions. The default is immutable, and if you want to make it mutable, you typically have to add a keyword. This is actually a good thing. It forces you as a developer to fall naturally into immutability unless you deliberately choose to make it mutable, which also serves, by the way, as a signal to the rest of the other programmers who will be looking at your code to say, yes, this value will change over time. Now, the other thing you notice, of course, is that x, y, and z don't have any types associated with them. Yet the compiler in a strongly typed language will know exactly what those are. They're integers. How do we know? Because that's what's on the right-hand side of the equals sign. Duh. What else could it be? Now, most languages will give you the opportunity to explicitly specify what x and y should be if it should be some kind of, if you want it to be a long, even though that's an integer constant, sure, they'll let you do that, a type descriptor. Typically, it'll be x colon long or something similar. Not always. Depends on the language. But the other thing then is our terminology changes up here a little bit. X and Y and Z are no longer variables because, yeah, they don't vary. They don't change. They are values. And this is a value binding to say that we are binding the value 0 to the value X, and we continue. Now, probably the most important aspect of any functional language is the idea that functions are first-class values. What that means is functions are things that we can use just like anything else in the language. You pass around integers all day long. Well, why can't you pass around functions as well? It makes total sense. It is a first-class value. It is something that the compiler understands intrinsically and is able to use, manipulate, etc. And what this will allow us to do is to capture some of these common operations and reuse them, but more importantly, allow us to pass logic around as easily as we would any particular datum. So for example, here I have a list of numbers. I know it looks like an array because it's square brackets, but we prefer lists because, again, we prefer immutability, and lists are actually better for immutable values than arrays are. So here I have a collection, a list of numbers, 1, 2, 3, 4, 5, and now what I want to do is I want to transform that list into a list of squares, meaning those numbers times themselves each time. So 1 times 1, 2 times 2, 3 times 3, etc. So here what I do is I take a function, which I've expressed right there directly in the code, and I apply it, that's the term, to each of those elements in the list, thus transforming each element in the list, then collecting them into a list and handing it back. And you say, dude, I could do that with a for loop. Why is this any better than what I do every day? And I will tell you this. What happens if that becomes a list of 5 million elements as opposed to 5? How's your for loop looking then? Because funny thing, that function, all that we really know, that map function, that transformer, all that we know it's doing is it guarantees it will apply this passed-in function to each element in the list. It does not guarantee that it will do so serially. As a matter of fact, depending upon how the packaging system works, that could easily be a parallel version of map that spins up, say, 50 to 500 to 5,000 threads, breaks the list up evenly across all those threads, applies the map across each part of that list, and then reassembles it. It's classic map reduce, except without the reduce. hence the name, MapReduce. And your code over here, in order to take advantage of that highly concurrent behavior, what do you have to change? Nothing. Because what I'm doing is effectively an inversion of control. I bet you didn't think you were going to hear that phrase in a functional programming talk. Because typically inversion of control has meant dependency injection, right? All that Spring goodness, garbage, whatever. We go to constructor injection, property injection, blah. Go talk to Josh Long. He'll talk your ear off about that stuff. This is why Martin Fowler never liked the term inversion of control to describe dependency injection, because the inversion of control can actually happen in a variety of ways. Here we're inverting the control as to who exactly is responsible for doing the squaring in the list. When you write a for loop, you have to do it. Here, we're letting the library do it based on logic that you've given it. It allows the code that you write to be executed in a different context. There's also this concept of partial application and currying, which is going to be very, very difficult for many Java, C++, C# developers, because we normally think, hey, if I have a function that takes 2 arguments, and I only give it 1 argument, what do I get? A compile error. Of course, duh. The function takes 2 arguments, strongly typed language. You have to provide 2 arguments to it, right? Not necessarily. Not if you're using a language that understands that functions, being first-class values, can actually be partially applied. Remember, the use of a function, we call it applying a function. So it can be partially applied by providing less than the full number of parameters. And the return from doing so is a function. So here, for example, I have a function add that takes 2 parameters, x and y. And now if I say I want to invoke add, but I only want to give it 1 parameter, the literal value 2, what I get back is a function that is expecting 1 parameter. As it turns out, if you take this to its logical extreme, everything is a function that takes 1 parameter. Because if I have a function that takes 3 parameters, I give it 1 parameter, and then it becomes a function that takes 2 parameters. I give it 1 parameter, and then it becomes a function that takes 1 parameter. And actually, if I take these functions that are all expecting 1 parameter and chain them, what we call currying, we get this really nice pipeline effect. But the end result of all of that composition, as we call it, is a function. It's the same kind of composition we do with objects, but we're doing it with logic, and we're not inheriting, and we're not owning, and yeah, okay, so it's not really at all like composition from the object world, except in the name, which is important. We tend to think of these languages as strongly typed, largely because, quite frankly, it's a lot easier for them to operate, it's a lot easier for them to work. We want them to be able to make inferences about our code. All of the examples I've shown you are strongly typed functional language because the compiler can figure out in each case what the type of the thing should be. And as a result, the compiler doesn't need you to tell it what those types should be. Compiler can do it on its own, hence type inference. If anybody's ever played around at all with C#, we see a limited form of type inference in C# using the var keyword for local variables. That's as far as they can go. If anybody's ever played around with Scala, you've seen type inference. If you've played around with Clojure, you've actually worked with one of the dynamically typed functional languages. Lisps intrinsically are dynamically typed as opposed to strongly typed. We also have a tendency to like recursion. This largely has to do, again, with this notion of immutability. If you are somehow iterating across a loop, and if you're keeping track of some sort of state, by definition, you're making local changes. This can create some problems. If, however, we recurse, we're actually keeping state on the thread stack itself, rather than in some variable which could potentially escape the thread and therefore be clobbered by some other thread. And so as a result, functional languages have a tendency to be very highly recursive. Now, normally, in languages like Java, C#, C++, etc., we dislike recursion because it tends to be more expensive than if we just do a for loop. Most of the virtual machines that we deal with today are actually implementing tail recursion optimizations so that they can see where what's called a tail call is taking place, where I recurse back into the same function, and they can actually unroll that. They can turn it, instead of a call to another stack frame on down, they can actually keep it all inside of one stack frame, making it just as fast as using a for loop, if not in some cases faster. One of the things that we also prefer about some of these functional languages is we prefer expressions as opposed to statements. Now, for a number of you, this is going to be kind of a wait, a what instead of a what? When we think about programming languages, as I said, this is a formal language. We need to define the terms of the language. So when we talk about an expression yields a value. So when I say 5, that is an expression. It yields the value 5. We prefer expressions. We prefer things that yield values. There's a kind of a long and rich history as to why they prefer that, but functional languages are actually pretty unified in this idea. So for example, when you look at Java, there are actually two forms of if. One is an expression and the other is a statement. The statement is the one that most of you are familiar with. If a curly brace do something else, curly brace do something else. That is a statement. It yields no particular value. If, however, you move over to Scala, for example, then if else is designed specifically to yield a value. I can say val result equals if, very similar to Java's question mark colon operator, the ternary operator, which says give me an expression, some Boolean value, question mark, expression, value, colon, other expression value, semicolon. One of those two will be returned as the result of this particular expression. We like expressions, largely because expressions very much stem from the field of mathematics, which is where a lot of these concepts basically came from. And expressions actually help in many respects because it gives us values to work with, we can chain them, etc. We also like tuples and lists. I've already talked about lists. We like them because they tend to be immutable more easily, particularly singly linked lists. I can peel off the head of a list. The remainder of it remains unchanged. Therefore, by definition, I haven't actually modified this list. I'm just pointing to a new head. But tuples, this is a concept you may not have run across before. A tuple is a very simple idea. It's an object with fields, no methods, and no names. If you've ever built a data transfer object, a DTO, you have built a tuple. And it turns out that tuples would be fantastically useful in a variety of places. For example, the JDBC result set is fundamentally a tuple. Actually, to be really, really technical about it, it's a list of tuples with some metadata describing the columns that the tuple fields each correspond to. We see tuples all the time in these functional languages. And in many cases, if you combine tuples with the idea that functions are first-class objects, meaning we can pass them around like data, and therefore I can put a function as a value inside of a tuple, we get dangerously close to objects without ever inventing any sort of explicit object-oriented paradigm. This is what Lisp has done for many years. This is what Clojure uses in a number of places, and so on and so on. Now, there's also, which is a little bit more beyond where I want to go today, there's this concept of pattern matching. Think of it as a switch, but it's a switch on steroids. But it's good steroids. You won't actually beat anybody up if you use it. Because I can use pattern matching not only to evaluate the value, but the type of the thing. I can put guard clauses on it, et cetera, et cetera, et cetera. There's also this concept of laziness, that I don't actually evaluate anything until I absolutely have to, which again is something that some functional languages choose to pass by. The more traditional languages, Haskell, for example, really embrace laziness as an important concept. But most of the other languages, F#, Scala, Clojure, they'll give you as much laziness as you want, but we actually kind of don't need a lot of it. Because one of the things that we do have are these notions of sequences. Streams is what Java 8 calls them. And we can do various things with these sequences. So for one of the classic examples in any functional programming language is that of a Fibonacci series, where you add the previous two numbers to get the current number. It's all the rage. If you do anything in the functional space, you will write a Fibonacci. It's like the hello world. It's like the C++ developers, we all had to write our own string class. And Java developers, we all had to write our own servlets. Well, functional programmers, you all have to write your own Fibonacci. It's just a thing, okay? And these sequences, they look and feel a lot like collections in a lot of ways. And you know what? Screw this. Screw this. Forget slides. Slides are boring. Who prefers slides over code? Yeah, if your hand is up, you are an architect. You just haven't admitted it yet. All right. So let's do this. I'm going to get stuff out of the way here. All right. So first of all, I have a classic person class. Is there any questions here? You're sure? Because there's a JavaScript talk going on somewhere. If you don't get this, you probably want to go catch that. Okay. And then we have a collection of persons here, right? Now, what I'm doing here is I'm just using the standard arrays as list to get them into a list of persons. And as a matter of fact, let me just make sure that it will, yep, yay, it all compiles. And again, one of the things that I would like to do, because I'm a very generous kind of person, right? Person, P in people. System.out.println, here, have a beer. Right? Compile that. Run it. Hey, everybody gets a beer. Yay! Don't you wish you were on this list? Except, there's a problem. Now, none of you know this, but that's my youngest son, Matthew. I don't want him to have beer for the very basic reason that at one point when I was asking Matthew to clean up some stuff in the kitchen, he ran across a bottle of scotch. This was probably about 3 years ago or so. And he said, "Hey, Dad, what's this?" And I said, "That's Scotch whiskey." And he said, "Oh, can I try some?" He's 13. And I thought, wait a minute, parenting moment. Parenting moment, right? Because when I was a little bit younger than him, my dad came back from a trip to Europe with a bottle of Chivas Regal and said, "Hey, would you like to try some?" And I tried some. And it burned all the way down. And it totally cured me of any desire to drink any hard alcohol until I met Neil Ford. So I thought, parenting moment. I said, "Matthew, would you like to try some?" He said, "Sure." So I took out a glass, and normally you pour like a finger for scotch. I gave him like a fingernail, just a splash. Here you go. He tries it. He goes, "Oh, that's good." Damn it! I did learn something important that day, that if you're going to do this with your children, do not use 25-year-old Macallan. Prefer Chivas Regal. So I don't want him to get beer. I think it's fairly self-explanatory. Why? So now what I can do is, of course, I can say, hey, if p.getAge is greater than 17, or wait, drinking age is 20 in the United States, okay? So now, compile, run, yay. Now, we could go through and do this exercise a couple more times, but fundamentally, I'm going to stand up here and tell you that this code is intrinsically unreusable. I can't reuse this code. If there is another place elsewhere in the code where I want to give everybody a beer, or if I want to test to see if everybody's capable of driving, or if I want to see if people are old enough to get retirement benefits, or if I want to find all of the Newards in this collection of people, or, every time I do a for loop, I am intrinsically writing non-reusable code. I am intrinsically violating dry. And so you say to yourself, I'm a smart programmer, I want to figure out how I can reuse some of that code. And so you will say, I'm going to create, in this case I'm going to copy just because I'm a little concerned of time. You will create let's see, there we go. You will create a class called lists. And this will be basically just a static utility class. And I'm going to grab this right here, so I don't have to type it. And this function here, this filter, is going to say, give me a list. That's what this first parameter is here. And then give me a function that knows how to take a particular type, a person, and return a Boolean, and I will walk through the list and see if that function returns true, and if it does, add it to the resulting list, and then return the set. Now again, I just accidentally bumped into, I want these results to be immutable, right? So here, whoops, when I go back to app, now I can say, all right, fine, list person drinkers equals list dot filter, and now I need to pass in a predicate. And actually, I think I have a predicate. Yeah, I do, but I've done that in terms of function 1, if I'm not mistaken. Yes, function 1. This is frequently, and matter of fact, in Java 8, this will be referred to as a predicate. Anything that returns a Boolean instead of an arbitrary value. Okay? So, we can look at that later if we need to. All right. So now function 1, this is a very simple interface. And again, something exactly like this appears in Java 8 now, so I don't have to use this if I don't want. But this way I can show you that there's nothing up my sleeves. There's nothing magical here. This interface consists simply of a function, and again, I use the name apply, because that's sort of the standard terminology that everybody uses. And it takes a parameter and it returns a result. This is pretty straightforward stuff, yeah? So that now, when I come back here and I say, all right, I want to use this filter, when I go into my app, I will say, fine, I want to, this will return a Boolean and it will take a person, like so. Let me swipe this out a little bit so we got a little bit more room to work with. Awesome. And then if p.getAge, actually I don't even need to do the if, I can simply say return p.getAge greater than 20. Oops. Oh, lists? Haha. See, this is why pair programming works, guys. And, oh, yes, thank you. Still cannot find the symbol lists.filter. Lists.filter. Let's see here. I don't think I need to do this, do I? Maybe I do. No, that gave me more errors. More errors, bad. Nope. What symbol can it not find? What have I, oh, did I not save that? That would be silly. Yeah, but none of you guessed it either. So, hey, look at that, yay. Now, one of the other things we can often do with these things, as I've said, is we can do some transformation to these guys. Matter of fact, let me just uncomment all of these, right? So that I can transform this thing from one thing into another. We've already seen map. We saw that earlier when we talked about how we were going to square the elements inside of a list. But we can also transform this thing from one thing to another. So for example, I can come back to app here, And I can say, all right, you know what I'd really like to do is I'd like to get a list of everybody's names. And in this particular case, I'm going to create a function that returns a string and takes a person, like so. So actually what I'll do instead, just to keep it a little bit easier, we'll do this with ages, just to extract the age out of it. This is actually what happens whenever you do a select in SQL. So I can simply say return like so. And then thank you. I knew there was something about that that bothered me. Like so. Oh, turns out I need one other thing from my templates. What happened to my tuples? Tuple2.java. Oops. Helps if you actually save it off. There we go. Cannot be applied because it wants list of R. Oh. Hey, just as a tip, by the way, don't do this. Don't put the list in the front and then in the back on everything else. That's just silly. So we'll transform like so. You know, having all these templates in a different directory seemed like such a good idea. Okay, so there we see everybody's age. And again, one of the things we can do with this is we can also do a reduction operation on this, which we call a fold. We start with some seed value, we take a list, and then we have an operation that takes a return value, takes the seed, takes the parameter, and what I return for this particular operation. In other words, I take a list, and I start folding the two values together in various ways. So for example, if I want a summation of all of the ages, so that, for example, I could divide by the number and get an average age or whatnot, this is actually one of the reduction style operations. So that now I can say integer total ages equals lists dot fold. We're going to start with a seed of 0, because that's where I want to begin whenever I'm adding something up together. And let's see, I'm going to pass in the people. And then I'm going to need another one of these functions whose job it will be to essentially add these up over time. Out, println, total ages. And there we see the total ages of everybody is 212. Yay, what an amazing demo. Except, you're all bored. No, it's okay. I totally get it. You're all bored. You're like, dude, I do more interesting things than adding up people's ages. I do important work. I do important work like take a collection of person objects and transform them into XML. That's what I do. I'm important. Well, shoot, screw you. I can do the same thing. we can actually start here. In this case, I'm going to do a string, take a person. And I'm not going to need this because the seed is actually going to be sufficient. And then public string apply, string current person P, return current plus person. How about we do this? Oh, I'm sure I'm missing a couple somewhere. Let's see. Oh, there it is. There we go. Oh, yes. I must have a close parens to close off the fold operation. And look at that. No soap. No Jaxby. Just simple functions. Because it turns out when we stop and we start to think about processes, behavior, functions as first-class concepts, and yes, I know one of you is sitting in the audience going, he forgot the quote marks on his attributes. That's not a compiling demo. Fine. Tell ya. Polish attendees, man. Oops. Oh! Just kidding. You happy now? Shut up! That's where my bad eval is going to come from. Because look, guys, fundamentally, all this functional programming stuff, it's just a different way of thinking about the world. It's just a different way of thinking about how we approach these problems. It's just about taking these things that we've used to call methods and extracting them on their own. And this is what makes it hard for the traditional object-oriented developer, is that we are accustomed to looking at the world to say, here we have state, and here we have behavior, and of course we combine them together to create this concept of an object. An object is not complete somehow unless it has both state and behavior. But when presented with all of these issues, with all of these problems, look at the Gang of Four book and you realize that none of those, very few of those are actually dealing with what we would consider to be domain objects. Most of the time, they're dealing with these ephemeral things, these rules, these strategies, ways in which to do double dispatch, et cetera, and so on. How to construct objects. I mean, the idea of using an object to construct an object it's weird when you start phrasing it that way. So the functional programming paradigm simply says, look, man, take the blinders off. Not everything has to be cast in terms of objects. Yes, objects are a useful property. They are a useful thing. It makes sense to model a significant part of the world using objects. But there is also this other concept, the notion of functional programming, the notice of the concept of, the promise of transformations, of capturing these operations and using them in some way, composing them. Now, my little pseudo-functional library up here, it lacks a bunch of stuff, including the idea of partial application. It would be great, for example, to take that function that transforms a single person and capture that as a function. And I can do it. I can certainly capture it off because Java has always had the ability to capture off these interface. Once I have an anonymous implementation like this, I can capture it off and store it as a reference to something. I would probably stick it on the person class since that has everything to do with persons, and then use it in various contexts. It's more work to do that because the Java language didn't support functions naturally. Now today, we actually can make a lot of this code go away through the use of the Java 8 syntax. But because that's not common yet, I chose not to use it. But one interesting exercise would, of course, be to transform this into something that's Java 8 specific and use the Java util function package. Make use of the function type, make use of the compose method that's present on the function type, make use of the predicate type that's present within that package, instead of building it yourself, because quite frankly, just like with a lot of the object libraries that are out there, it's far better to let somebody else build it, debug it, test it, etc. Oh, and by the way, since we're talking about testing, let's look at this code here. And let's look at all the places that I really should be thinking about testing. So for example, this idea of filtering out, well, assuming that filter works for any arbitrary list, it's already tested for every possible list. And how many of you would sit down and write a series of test cases for get age greater than 20? I'm sure somewhere in the back somebody's saying, well, TDD says, because, you know, the greater than sign might be broken. And if that's the case, folks, you have bigger problems. Just saying. A functional approach, because it tends to prefer small atomic functions like this, is actually ridiculously easy to test. Okay, I want to capture off this drinking age filter. Great, I capture it off, I'll store it as an instance of a function 1 somewhere, and then I'll test it with like maybe 3 cases if you want to get really, really crazy about it. I'll do like 19, 20, and 21. Because the funny thing about integer math is all the other cases would more or less be taken care of at that point. Down here, p.getAge. Just as a reminder, getAge consists of return age. Where's my TDD guy who's going to argue with that? I mean, at the end of the day, how much can you really test some of this stuff? It is built off of some of the basic primitives within the language. So your testing burden all of a sudden becomes negligible. And yet, we're building up these little tiny atoms into larger molecules. We're composing functions into larger functions to the point where by the end of this, we have successfully transformed a collection of persons into an XML stream suitable for shipment as part of a SOAP envelope. You could do the exact same thing with JSON. Matter of fact, you know exactly where you would do it, right there in that apply method. Just simply put some JSON syntax around it and voila, you now have the ability to transform to both XML and JSON via the use of only one function for each without violating encapsulation. Put that in your pipe and smoke it SOAP. Ooh. Where does this take us? Where does this leave us? Well, the concurrency thing is a big deal. We have lots and lots of cores that want to operate in parallel. And if, for whatever reason, this serial fold that I've got here doesn't work for you, you could always create a P fold, which does it in parallel, which makes use of all of that powerful Java threaded executor stuff, and run this over a series of different threads. And again, because this does not affect the original, remember I'm returning a new list, that means that you get a new copy back, which means that the original is not modified, which means people could still be using the original. There's no lock that needs to be had here, unless you really want to make sure that nobody can be modifying the oh wait, if they're immutable, they can't be modifying them, which means your locking burden, your synchronization burden has now dropped to basically nil. Whenever we start talking about functional programming, concurrency is typically the first place people go. Oh yeah, concurrency, man, that's why you want to do functions. Look, guys, if the concurrency thing is big, I won't shirk away from it. But at the end of the day, a lot of you do a lot more with collections than you do with concurrency. Collections are the gateway drug to becoming functional programmers. So even if you're not in a position where you can adopt Scala, or you can just take up Clojure, or you really want to play around with Frege, which is a Haskell variant that runs on top of the JVM, you don't want to take up a new language and learn new syntax? Fine. Java 8 has you covered. Do this in Java 8. Get your feet wet with this functional stuff, and I guarantee you, you will never program the same way again. Peace. Bye.